Hello there, and welcome. If you're someone who likes to unwind by thinking about stars, planets, and the quiet beauty of space, you're in the right place. Tonight, we're leaving our solar system behind and drifting into the darkness between the stars, where other planets orbit distant suns and almost anything is possible. We'll visit worlds that rain metal, planets made of ice and fire, and lonely giants drifting through space with no star at all. Some of what you'll hear might sound impossible, but all of it is real. And if you enjoy these sleepy journeys, you're welcome to like and subscribe. It helps others find their way here too. But for now, get comfortable. Let your body rest. Let your thoughts wander. And let's begin. There are planets with temperatures hotter than stars. Stars are known for their incredible heat, glowing plasma furnaces burning millions of degrees. But believe it or not, some planets come close. One such world, Kelt 9b, reaches temperatures over 7,000 degrees Fahrenheit, hotter than many red dwarf stars. This gas giant orbits so close to its massive blue star that it completes a full orbit in just over a day. The planet is tidally locked, with one side facing the star permanently, absorbing a relentless barrage of radiation. Its atmosphere is being torn apart, streaming into space like a comet's tail. The heat is so intense that molecules break apart and metals can vaporize. It's not just hot, it's extreme beyond comparison. These ultra-hot Jupiters challenge what we thought planets could be. They blur the boundary between planet and star, blazing, storm-racked infernos that last only briefly before dissolving into the darkness. Some planets might be made almost entirely of diamond. It sounds like science fiction, but under the right conditions, it could be real. Some exoplanets, especially those rich in carbon, might form in ways that produce planets composed largely of diamond. If a planet forms around a star with more carbon than oxygen, the ingredients available during its birth can lead to carbon-rich structures. One candidate is 55 Cancri E, a super-Earth twice the size of Earth that may contain an enormous amount of carbon under intense pressure. That pressure, deep within the planet's interior, could create vast regions of crystalline diamond. It wouldn't glitter or sparkle the way we imagine. There would be no jewelry here, just darkness, heat, and unimaginable density. Still, the idea is captivating. A planet forged from carbon. A world where the mountains may shine with buried crystal. A place where geology becomes something almost otherworldly and precious. Some exoplanets orbit two suns, like Tatooine in Star Wars. In science fiction, we've long imagined twin sunsets, two stars sinking beneath a distant horizon. But now we know those strange skies might actually exist. Some exoplanets don't orbit a single star, like Earth does. They orbit two. These are called circumbinary planets, and they move in beautiful, complex loops around pairs of suns that orbit each other. When the stars are close together, a planet can circle them both as if they were one. But if the stars are farther apart, the planet might orbit only one, tugged and tilted by the other's distant gravity. The result is a world with unusual light cycles, changing seasons, and double shadows. These systems are rare and delicate, but they do exist. So the sky of some distant world may truly glow with two dawns and two dusks, a sky once imagined in fiction, now quietly confirmed by science. There are planets where it rains molten glass. Some worlds are so alien that even their weather defies the imagination. Take HD 189,733b, a gas giant larger than Jupiter, orbiting so close to its star that it completes a full orbit in just over 2 days. The planet's atmosphere is scorching, with temperatures around 700 degrees Fahrenheit. Winds whip around it at thousands of miles per hour, and suspended in its blue, hazy skies are tiny particles of silicate, the building blocks of glass. When conditions are right, these particles condense and fall as rain. Not water, not ice, but molten glass, swept sideways by high-speed winds. From far away, this planet looks strangely Earth-like in color, a soft blue shimmer, glowing near its sun. But up close, it's a storm-racked furnace, beautiful, violent, and utterly uninhabitable. It's one of many exoplanets that remind us nature's imagination reaches far beyond our own. Others may be covered in oceans thousands of miles deep. Some exoplanets might be ocean worlds, planets almost entirely covered in water. No continents, no islands, just endless global seas. These aren't like Earth's oceans, which only reach a few miles deep. On these worlds, the water layer could be hundreds or even thousands of miles thick. At the surface, it might be calm, windblown, or stormy. But deep beneath, the pressure would rise to incredible extremes, creating exotic forms of ice. Not the kind we know, but dense, high-pressure ice that forms under crushing weight. These planets may have rocky cores at their centers, hidden far beneath the water. Some may even have liquid layers warmed by internal heat. Could life exist in such oceans? We don't yet know. But ocean worlds may be more common than we thought. Gentle, glistening planets with no land in sight, quietly turning in the dark, far from any sun we know. Some planets are tidally locked. One side always faces the star. Not all planets spin like Earth does. Some are tidally locked, meaning one side of the planet always faces its star, while the other remains in permanent darkness. The same thing happens with our moon. We only ever see one side. But imagine this on a planetary scale. One hemisphere scorched by unending daylight, while the other is trapped in eternal night. Between them lies a twilight zone, a ring around the planet where the light is always low, and the temperature might be just right. Some scientists believe that in certain cases, life could survive in this thin band of balance. These planets may have fierce winds, strange cloud formations, and wild extremes in weather. But they're real, and they challenge our ideas of what makes a world habitable. Life, if it exists, might learn to thrive in the shadows, or just on the edge of the light. Hot Jupiters skim so close to their stars, their atmospheres boil off. Imagine a planet like Jupiter, massive, gaseous, and immense. Now move it far closer to its star. So close that a single orbit takes only days. So close that temperatures rise beyond 2,000 degrees. These are hot Jupiters, giant planets that skim just above their star's surface, so near that their upper atmospheres are literally being blown away into space. We've discovered many of these strange worlds, often among the first exoplanets we ever detected. Their sheer size and tight orbits make them easier to spot, but they're deeply mysterious. How did such massive planets get so close to their stars? Did they form there? Or were they pushed inward over time by gravitational forces? Some trail glowing tails of gas like comets. Others are slowly shrinking as their atmospheres evaporate. They're unstable, dramatic, and often short-lived. Brief flashes of planetary fire, circling faraway suns. Some exoplanets are darker than charcoal. Not all planets reflect light the way Earth does. Some absorb nearly everything, becoming darker than paint, darker than ash, darker even than charcoal. One such world is TRES2b, a gas giant orbiting a star about 700 light-years away. Its atmosphere reflects less than 1% of the light that hits it. Scientists aren't entirely sure why. It could be due to vaporized alkali metals or unknown chemical compounds in its upper layers. Whatever the cause, the result is extraordinary. A planet as dark as coal, glowing faintly with heat, nearly invisible in reflected starlight. Even its night side, already in darkness, is only slightly cooler than the day. If you could stand nearby and look toward it, you might see only the faintest silhouette against the fire of its star. A nearly perfect shadow, orbiting in silence, absorbing the light of the universe. We found planets floating alone, without a star. Most planets orbit stars, but not all. Some are wanderers, free-floating planets that drift through space alone, unbound by any sun. These are known as rogue planets, and we've found evidence of dozens, maybe hundreds, across the galaxy. They might have formed normally, then been ejected from their home systems by gravitational disruptions. Or they may have formed in isolation, like failed stars, never capturing enough mass to ignite. These worlds are dark, cold, and incredibly difficult to detect. But with powerful infrared telescopes, we can catch hints of their faint thermal glow. Some might still hold internal heat, keeping subsurface oceans warm for billions of years. Others could be completely frozen, drifting forever through the black. A planet without a sunrise. A world with no sky. And yet, even here, the quiet question persists. Could something live in such stillness? Some worlds may have ruby and sapphire clouds. When we think of clouds, we imagine water vapor, soft, pale, ever-shifting. But on some exoplanets, the skies may shimmer with gems. On scorching hot gas giants, where temperatures soar above 2,000 degrees, minerals that would be rock on Earth can vaporize, rise into the atmosphere, and condense into clouds. Aluminum oxide, iron, titanium, and in some cases corundum, the mineral form of rubies and sapphires. These mineral clouds may scatter light in strange ways, tinting the skies red, purple, or deep blue. On one such planet, PAT P7b, researchers have seen shifting patterns in the atmosphere that suggest high-altitude mineral clouds sweeping across the sky. It's hard to picture a world wrapped in heat and storms, lit by a blazing sun, with clouds of liquid gems glinting and swirling overhead. The universe is stranger and more beautiful than we can easily imagine. There are super-Earths that could be more habitable than Earth. Some exoplanets fall into a category called super-Earths. rocky planets larger than Earth but smaller than Neptune. They may have stronger gravity, thicker atmospheres, and more stable climates. And some of them may be even more hospitable to life than our own world. One such candidate is Kepler 442b, a rocky planet in the habitable zone of its star, not too hot, not too cold. It receives just the right amount of sunlight and may have the mass needed to hold onto an atmosphere and liquid water. Some super-Earths could have deeper oceans, fewer tectonic disruptions, and greater surface stability, all conditions that might help life emerge and endure. Of course, we don't know yet if any of these planets are truly habitable, but they remind us of something humbling. Earth may not be the perfect planet, just the one we happen to call home. We've seen planets that orbit in just a few hours. Most planets take months or years to complete an orbit around their star. Earth takes 1 year. Mercury, the fastest planet in our solar system, takes 88 days. But some exoplanets move much, much faster. We've found worlds that orbit their stars in a matter of hours. One of the fastest is Kepler 78b, a planet just slightly larger than Earth that completes a full orbit every 8.5 hours. It's so close to its star that its surface is likely covered in molten rock. Temperatures reach several thousand degrees. These ultra-short period planets are often tidally locked, their days and nights frozen in place. Their stars loom huge in the sky. Gravity pulls at their structure, and some may be slowly tearing apart. These planets are extreme, fast, hot, and fleeting. But they exist, skimming the edges of their stars like sparks flying from a flame. Other planets take centuries to complete one orbit. While some exoplanets race around their stars in mere hours, others take their time. Long, silent journeys that can last for centuries. One of the slowest moving planets we've found is Gu Piscium b, a gas giant that takes about 1,000 years to orbit its star. Its orbit is so distant that it's barely held by gravity. If it were any farther, it might break free entirely. These long-period planets are incredibly hard to detect. We can't wait 1,000 years to watch them complete a loop. Instead, we catch them in motion, a curved path, a long arc, a hint of something vast. Some of these planets may have cold, dark surfaces, illuminated only faintly by starlight. Others may experience seasons that last lifetimes. On such worlds, change is measured not in years, but in generations, a slow and silent rhythm far beyond our own. We've discovered thousands of planets beyond our solar system. For most of human history, we only knew of one planetary system, our own. The sun, the moon, and the wandering stars that moved through the sky. But everything changed in the 1990s when the first exoplanets were confirmed. Now, thanks to space telescopes like Kepler and TESS, we've found thousands. Planets around distant suns. Some small, rocky, and Earth-like. Others massive and strange. Some orbit tightly in just a few days. Others take centuries to complete a single trip around their star. Each discovery reshapes what we thought was possible. And still, this is just the beginning. We believe there are hundreds of billions of planets in our galaxy alone, more planets than stars. Worlds upon worlds, quietly orbiting in the dark. We'll never reach most of them, but we can listen for them, measure their shadows, and wonder what else might be waiting out there. We've detected planets using the shadows they cast during transits. The light from a star is usually steady, but sometimes, just briefly, it dims. A tiny dip, a momentary flicker. That dimming can mean a planet has passed in front of it. This is called the transit method, and it's one of the most powerful tools we have for finding exoplanets. When a planet crosses its star from our point of view, it casts a faint shadow, not in the dramatic way we see with eclipses, but in subtle drops in brightness, often less than 1%. Space telescopes like Kepler and TESS have used this technique to find thousands of exoplanets. From just those shadows, we can learn the planet's size, orbit, and even hints about its atmosphere. We're watching stars blink ever so slightly to learn about unseen worlds. The light of a distant sun interrupted by the quiet silhouette of a planet far away. Others were found by the gravitational wobble they induce. Even a planet's gravity can leave a fingerprint. When a planet orbits a star, it doesn't just move around the star, it causes the star to move slightly too. This wobble is tiny, but it's real. As the star shifts back and forth, its light shifts with it, squeezed and stretched by motion. Astronomers can detect those changes using spectroscopy, breaking starlight into its components and looking for the subtle signatures of motion. This is called the radial velocity method, and it was how the first exoplanets were discovered. It works best for massive planets close to their stars, like hot Jupiters, but it's also helped us find multi-planet systems and long-period orbits. We're not seeing the planets directly, we're watching their stars sway under their pull. Like a dance too distant to see, but close enough to feel in the music of the light. Some exoplanets appear to have atmospheres escaping into space. A planet's atmosphere is never truly still. Winds blow, clouds drift, particles escape. But in some extreme cases, the entire upper atmosphere may be drifting away, leaking into space like breath into the void. This is especially common in hot, close-in gas giants, where intense radiation from the nearby star can heat the outer layers until they reach escape velocity. These planets can develop long, comet-like tails of escaping hydrogen and helium. We've seen this in several exoplanets, where ultraviolet light reveals trails of gas streaming behind them. Some planets may lose significant mass this way over time. Others might be stripped down to rocky cores. This process helps shape the evolution of planetary systems, showing how stars can sculpt, reshape, or even destroy their planets. It's a reminder that even worlds can change, erode, and fade, leaving only their gravity behind. We've found planets in star systems with 3 or more suns. Not every star system is like ours. Some contain not 1, but 2 or 3 or even more stars orbiting together. And in a few of these complex systems, we've found planets. Imagine a world where the sky is never dark, where shadows stretch in different directions, where one sun rises while another sets. These planets must follow delicate, stable paths to survive the tangled pull of multiple stars. Some orbit closely around a pair of stars, circumbinary planets, while others orbit far beyond the entire cluster, tracing wide loops around a chaotic center. The lighting would be strange, the seasons unpredictable, and the sky full of motion. Yet these planets exist. and they remind us that planetary systems can form in ways we never expected. Even in places where gravity is complicated and the night sky never settles, planets find a way. Some worlds orbit the collapsed remains of dead stars. Stars don't live forever. Some end their lives as white dwarfs, small, dense remnants of stars like our Sun. Others collapse into neutron stars, or even black holes. And around some of these stellar corpses, we've found planets. These worlds orbit what remains after a star has died, glowing embers or pulsing remnants of stellar fury. In some cases, they're survivors, somehow enduring the chaos of a supernova. In others, they may have formed from the debris left behind, rising from ashes into something new. The light from these stars is dim, cold, or distorted, but the planets remain, tracing silent paths through a kind of stellar graveyard. Some are blasted by radiation. Others drift quietly, circling dead suns in eternal twilight. It's haunting and beautiful. A reminder that even after the end, something new and strange may begin again. One planet orbits its star backwards. Most planets orbit in the same direction their star spins. That's how solar systems usually form, from a single swirling disk of gas and dust. But nature doesn't always follow the rules. We found at least one exoplanet, WASP 17b, that orbits its star in the opposite direction. Instead of moving with the star's rotation, it pushes against it. This backwards orbit likely formed through chaos, a near collision, a gravitational shove, or some violent rearrangement long ago. It's massive, bloated, and blisteringly hot, orbiting close to its star every few days. The fact that it moves in reverse challenges our understanding of how planetary systems evolve. And it proves something important. The universe is more flexible, more chaotic, and more surprising than any single theory. Some planets follow the flow. Others push against it. And some, like this one, move through the cosmos with quiet defiance. We've seen signs of clouds on planets light years away. It may seem impossible, but we've detected signs of clouds on exoplanets dozens, even hundreds of light years away. Not by seeing them directly, but by studying the way starlight passes through a planet's atmosphere during transit. As light filters through the edge of an alien world, some wavelengths are absorbed, while others pass through or scatter. And this delicate fingerprint tells us about the gases, molecules, and particles suspended in the air. In several cases, the data suggests the presence of clouds. Not white, cottony clouds like on Earth, but dark, metallic, or mineral-based clouds made from silicates, iron, or exotic chemicals. These clouds might reflect or block starlight, shaping the planet's appearance and temperature. Some planets are permanently cloud-covered. Others show changing patterns across their skies. We can't yet see these worlds, but we can read their weather from starlight alone. Some exoplanets orbit closer to their stars than Mercury does. Mercury is already scorching, the closest planet to our Sun, bathed in light and stripped of atmosphere. But some exoplanets orbit much closer to their stars, at distances where no planet in our solar system could survive. These worlds complete orbits in mere hours or days. Their surfaces may be molten, their atmospheres whipped away by stellar winds. Some are tidally locked, with one side blistering in unending daylight and the other frozen in eternal darkness. Others are so close they bulge from tidal forces, stretched like teardrops by their star's gravity. These extreme planets challenge our ideas of habitability, yet they're among the easiest to detect, thanks to their short orbital periods. Many of the first exoplanets discovered were in this category. They're hot, fast, and often unstable, but they show us just how flexible and extreme planetary systems can be. Others drift far beyond the reach of any sunlight. Not all planets huddle close to their stars. Some orbit so far away that sunlight becomes a faint and feeble glow. These distant worlds may take hundreds or even thousands of years to complete a single orbit. Temperatures plummet. Seasons span generations. And in the deepest cold, chemical reactions may slow to a crawl. Yet even here, planets persist, silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants, wrapped in frozen clouds. Others could be rocky and barren, crusted over with ice and carbon dust. And some may have hidden warmth beneath the surface, sustained by radioactive decay or ancient heat trapped from formation. These far-flung orbits are hard to detect, but their existence reminds us that planets can survive in places we once thought empty. Even in the loneliest reaches of space, a world can quietly endure. There are planets with spectacular hypothetical ring systems. Saturn's rings are beautiful, delicate bands of ice and dust, suspended around a gas giant. But they may not be the most impressive rings in the universe. Some exoplanets appear to have rings that are thousands of times larger, stretching across vast distances, wide enough to eclipse their host stars. One candidate is J1407b, a giant planet or brown dwarf that may be surrounded by a ring system over 200 times larger than Saturn's. These rings could be made of ice, rock, or dust, possibly the remnants of forming moons. As the planet orbits, its rings may cast deep shadows on the star, creating strange dips in light that we can detect from Earth. If such a planet were placed in our solar system, its rings would stretch across the night sky. They're hypothetical for now, but their shadowy presence hints at the grandeur still waiting to be confirmed. We've only just begun to scratch the surface. For all we've learned about exoplanets, we're still at the very beginning. The first confirmed discovery was made in 1992. In cosmic terms, that's barely a heartbeat ago. Since then, technology has leapt forward. Thousands of planets have been found, and thousands more await confirmation. We've detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. But we've barely begun to understand what these worlds are truly like. We can't yet see their surfaces. We don't know what they smell like, sound like, or feel like underfoot. We can't say which ones have clouds, continents, or creatures. The truth is, every new exoplanet we discover is a doorway to something we've never seen. And as our tools grow sharper, the picture will only grow stranger, richer, and more full of wonder. The cosmos is full of planets, and we've only just knocked on the door. Some planets orbit so close they're slowly being vaporized. For some exoplanets, being close to a star is more than just hot, it's destructive. These planets orbit so near their suns that the intense radiation and stellar winds begin to strip them apart. The outer layers of their atmospheres heat up, expand, and gradually evaporate into space. Some form long, glowing tails of gas that stretch behind them, like comets caught in eternal retreat. Over time, these worlds lose mass, slowly shrinking, thinning, or transforming entirely. One planet, Kick 12,557,548b, may be crumbling under this kind of erosion, its surface shedding dust and debris with each orbit. It's like watching a planet dissolve in slow motion. These aren't just places to live, they're dynamic systems, constantly reshaped by their environment. Even something as vast as a planet can be worn away, little by little, by the unrelenting light of a star. We've discovered worlds that defy all expectations. Every time we think we understand planets, the universe hands us something we can't explain. We've found planets where the skies shimmer with vaporized metal. We've found rocky worlds hotter than lava, and giant gas planets colder than deep space. We've seen worlds with tilted orbits, backward spins, and rings so large they could block out a star. Some planets are too dense, others are too fluffy. Some shouldn't exist at all, at least not according to our models. But they do. Each strange discovery forces us to rethink how planets form, how they evolve, and what might be possible. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet contradictions, little cosmic puzzles scattered through space, waiting for someone to notice them and wonder. Some exoplanets might be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, just endless ocean, stretching in every direction. These are water worlds, exoplanets, where the surface may be completely covered by liquid water. Not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would be intense, enough to compress water into exotic ices and crush rock into unfamiliar forms. Some of these worlds might have atmospheres rich in steam or clouds of vapor circling overhead. Others could be wrapped in hazy mists, warmed by sunlight or internal heat. If life exists on these planets, it would evolve in a deep, sunless sea, shaped by currents and chemistry rather than light. We haven't confirmed one yet, but the evidence is growing. And if Earth is one kind of habitable world, then perhaps these dark oceans are another kind entirely. We've found mini-Neptunes, small but swollen with gas. Not every planet falls neatly into the categories we know. Between Earth and Neptune lies a curious group of worlds called mini-Neptunes. They're bigger than Earth, but smaller than our ice giants, and many are wrapped in thick layers of gas. These planets likely have rocky or icy cores surrounded by envelopes of hydrogen, helium, and other gases. They may look similar to Neptune from a distance, but inside, they could be wildly different. Some may have deep, boiling oceans beneath their clouds. Others might have no solid surface at all. They're too small to be true gas giants, but too big to be rocky super-Earths. For a long time, we didn't even know if planets like this could exist. Now we know they're common, possibly the most common type of planet in the galaxy. Strange, swollen, and still mysterious, they fill in the space between what we expected. Some planets are puffed up like balloons. Some exoplanets are so inflated they seem lighter than they should be. These puffy planets are large in size but low in density, huge soft worlds that could float in water if they were somehow dropped into a bathtub the size of a star. One example is WASP-17b, a gas giant twice the size of Jupiter but with only a fraction of its mass. These planets likely formed far from their stars, then migrated inward. Now, intense heat from the star causes their atmospheres to swell and expand. Radiation from the star may be breaking apart molecules, adding to the planet's strange properties. Some puffy planets have visible tails of escaping gas. Others seem impossibly light for their size. We still don't fully understand them, but they show how elastic a planet can be. Not rigid and fixed, but soft, unstable, and stretched by light. There are exoplanets with days longer than their years. On Earth, one day and 1 year are very different things. We spin on our axis once every 24 hours, but it takes 365 days to orbit the Sun. Not so for some exoplanets. In certain cases, especially for planets orbiting very close to their stars, the time it takes to rotate is longer than the time it takes to complete an orbit. That means the planet completes a full loop around its star before it even finishes turning once. These planets are usually tidally locked, with one side permanently facing their sun. The night side remains in darkness, frozen and still, while the day side burns under endless daylight. There's no sunrise or sunset, just one eternal face to the light. On such a world, the idea of time itself begins to blur. A day that never ends. A year that races by. A sky divided forever in two. Some worlds may be covered in thick, hazy skies. We often imagine alien worlds with clear skies and stunning views. But some exoplanets might be wrapped in thick layers of haze, blocking the light and obscuring everything below. These hazes can be made of complex hydrocarbons, photochemical smog, or exotic clouds of unfamiliar chemistry. On Earth, we see this kind of effect in places like Saturn's moon Titan, where a golden fog hides the surface from view. On exoplanets, especially those orbiting cooler stars, ultraviolet light can trigger strange reactions in the upper atmosphere, building up thick, murky layers that trap heat and scatter light. These planets may look dull or muted from space, their colors softened by haze. But beneath the clouds, oceans might churn. Winds might scream, and alien landscapes may wait in silence. We can't see them clearly, not yet, but we know the haze is there, a veil drawn over distant, hidden worlds. We've seen evidence of winds whipping at thousands of miles per hour. Weather doesn't just happen on Earth. On many exoplanets, especially large gas giants, atmospheric winds can reach extraordinary speeds, far beyond anything seen in our solar system. Some exoplanets are tidally locked, with one side always facing their star. That intense permanent heat creates powerful thermal gradients that drive fierce winds around the planet's atmosphere. Using space telescopes, astronomers have detected signs of winds blowing at up to 5,000 miles per hour, fast enough to travel the width of the United States in under an hour. These winds can shift clouds, reshape heat patterns, and carry vaporized metals across the planet. Some even redistribute light itself, shifting the brightest part of the planet away from where the star's light hits directly. It's invisible to the eye, but written into the glow of the planet's light, a whisper of motion in a faraway sky. Some planets could be tidally heated from the inside. Not all heat comes from a star. Some exoplanets, especially those in eccentric orbits, may be heated from the inside out, thanks to tidal forces. As they move through varying gravitational pulls, their interiors stretch and flex, creating friction and warmth deep below the surface. This is how Jupiter's moon Io stays volcanically active. And it may be happening on exoplanets too. Planets orbiting close to large stars or courting gravitational dances with neighboring planets can experience this kind of tidal heating. In some cases, it could melt rock into magma or keep subsurface oceans liquid beneath thick shells of ice. These planets might look cold or dark on the outside, but inside they're alive with motion. Heat without sunlight. Activity without a star. It's a reminder that energy can come from within, and that even in the outer reaches of a system, a planet may still be warm. We've discovered planets in ancient star systems. Some stars are nearly as old as the universe itself, formed in the galaxy's earliest chapters. And around a few of these ancient stars, we've found planets. They've been orbiting for billions of years, far longer than Earth has existed. One example is Kepler 444, a star system over 11 billion years old, with 5 small rocky planets. These worlds are from a time when the universe had fewer heavy elements, suggesting they may have formed from different materials than Earth. What might such planets be like? Could they be worn smooth by eons of impacts? Could they have once supported life, long before life began here? We may never know. But these ancient systems remind us how long planets can last, surviving stellar storms, galactic tides, and the slow march of time. They are cosmic elders, quietly circling in the deep past, still here, still turning. Some exoplanets may have moons we've yet to find. Where there are planets, there may also be moons. And yet, for all the exoplanets we've discovered, exomoons, moons orbiting planets outside our solar system, remain elusive. They're hard to detect. Small, subtle, often hidden in the noise. But we've seen hints. Tiny variations in a planet's transit, wobbles in timing, dips in brightness that don't quite match the model. One candidate, a possible moon orbiting the gas giant Kepler 1625b, is still under study. If confirmed, it would be huge, larger than any moon in our solar system. But even smaller exomoons could be important. They might stabilize planetary climates, shape tides, or even provide sheltered environments for life. Some moons could have subsurface oceans, like Europa or Enceladus. Others might be rocky and cratered, drifting in twilight above gas giants. We haven't seen them clearly yet, but they're likely out there, circling in the quiet, waiting to be found. Others could have entire moon systems of their own. Just as planets orbit stars, moons orbit planets, and for massive exoplanets, especially gas giants, it's likely they have entire systems of moons. In our solar system, Jupiter and Saturn each have over 80 moons, ranging from tiny captured asteroids to massive worlds with subsurface oceans. Now imagine a gas giant, many times more massive than Jupiter, orbiting a distant star. It could have dozens, perhaps hundreds, of moons, a miniature solar system all its own. Some moons might be rocky and cratered. Others could have icy shells or thick atmospheres. A few might even orbit in the habitable zone of their parent planet, shielded from stellar radiation and warmed by tidal forces. We haven't confirmed any of these exomoon systems yet, but the potential is staggering. Not just planets, but whole families of worlds drifting together, locked in gravitational harmony, far from home. Some exoplanets might support life, but not as we know it. When we imagine alien life, we often picture Earth-like conditions, blue skies, liquid water, and a comfortable temperature range. But life might not need any of those things. Some exoplanets could host life in environments wildly different from our own, in acidic clouds, beneath ice-covered oceans, or in high-pressure atmospheres thick with methane. Even life that doesn't rely on water, or carbon, or DNA. Extremophiles on Earth already live in boiling acid pools, radioactive caves, and near volcanic vents with no sunlight. So, on distant planets, it's possible that life could take stranger forms. Not walking, talking creatures, but microbial networks, chemical colonies, or self-replicating systems that thrive in environments we would find deadly. We may never meet them, but if we listen closely, in the light and shadow of alien worlds, we might someday find the first faint signature, a chemical imbalance, a breath of something living. We've found planets that barely skim the edge of being stars. There's a line between planet and star, and some exoplanets sit right at the edge. These are giant objects called brown dwarfs or super-Jupiters. They're massive enough to fuse a little deuterium in their cores, but not enough to sustain the fusion reactions that power real stars. They glow faintly with leftover heat from their formation, and some may even emit infrared radiation. One such object, called HD 100,546b, is so large and hot, it may straddle the boundary between planet and failed star. We're still debating where the cutoff lies. How massive can a planet be before it becomes something else entirely? These in-between worlds may form like planets or like stars. We don't always know which, but they remind us that categories in space are often blurry. The cosmos is full of edges that shimmer and shift, where one thing slowly becomes another. Some worlds lie right on the edge of the habitable zone. The habitable zone is often called the Goldilocks zone, the range around a star where temperatures are just right for liquid water. But many exoplanets lie right at the edge of this zone, where conditions are more uncertain. Too far out, and water freezes. Too close in, and it boils away. But on the boundary, things become more complex. A thick atmosphere might trap heat. A high reflectivity might keep a planet cool. And seasonal shifts or orbital eccentricity could cause dramatic climate swings. One hemisphere might be habitable while the other remains too cold or too hot. Life could exist only in pockets, beneath the ice, in deep caves, or around volcanic vents. These edge worlds are neither fully comfortable nor completely barren. They're places of tension and potential, where the balance between warmth and cold, light and dark, could tip either way or hold, just barely. We're learning to study the chemistry of alien atmospheres. Until recently, the idea of analyzing the atmosphere of a planet light years away seemed impossible. But now, thanks to precise instruments like the James Webb Space Telescope, we're starting to do exactly that. When an exoplanet passes in front of its star, some of the starlight filters through the planet's atmosphere. That light carries subtle fingerprints, spectral lines, from the molecules in the air. By breaking the light apart and analyzing those lines, scientists can detect water vapor, carbon dioxide, methane, and more. We can begin to guess at clouds, pressure, and even temperature. In some cases, we may even spot biosignatures, chemical hints that life might be affecting the atmosphere. It's like reading a message from across the galaxy, hidden in the colors of starlight. We're still early in this work, but with each new spectrum, we get a little closer to understanding what alien skies are truly made of. Some exoplanets may have seasons that last for decades. On Earth, our seasons are defined by a tilt, a gentle lean that changes the angle of sunlight across the year. But on some exoplanets, the mechanics are more extreme. A larger tilt, a stretched orbit, or multiple stars can create wild seasonal effects, with summers that last for decades and winters that span entire lifetimes. A planet might swing close to its star, warming dramatically, then drift away into a deep, frozen hibernation. Others might have chaotic seasons, shifting unpredictably with every orbit. Long summers could allow life to bloom, only to vanish beneath decades of cold. Or entire generations might live and die within a single spring. The rhythm of life, if it exists, would follow a different kind of calendar, written not in days or years, but in slow arcs and stellar dances. On these worlds, time moves differently, and so might everything else. Others might experience eternal twilight. Some exoplanets may live forever in the in-between, a place where day never fully breaks and night never completely falls. This can happen on tidally locked planets, where one side always faces the star and the other never does. But between these extremes lies a thin region called the Terminator, a ring of perpetual twilight. Here, the sky might glow dimly forever, caught between burning light and endless dark. The temperature could be more stable, the winds more moderate. If life exists, it might flourish along this twilight boundary, a narrow band of gentle shadows and muted warmth. There would be no sunrise, no sunset, just the soft, slanted glow of a star locked at the edge of the sky. A planet with a horizon that never moves. A place where time drifts in half-light and nothing ever truly sleeps. We've discovered planets locked in orbital resonance with each other. In some star systems, planets don't just orbit independently, they move together in quiet synchrony. These are called orbital resonances, where the timing of their orbits aligns in whole number ratios. For every 2 orbits one planet makes, another completes exactly 3. This balance keeps them from colliding and helps stabilize their motion. We've seen this in our own solar system, among Jupiter's moons, for example. But we've also found exoplanetary systems with long chains of resonance involving 3, 4, or even more planets. It's like a cosmic symphony, with each world playing its own rhythm, separate, but always in harmony. These arrangements are delicate. A small change in gravity or motion could throw everything off. But instead, they hold, gently, beautifully, orbit after orbit. The universe, it seems, is not just chaotic, it's also deeply musical. Some planets show mysterious signals we still don't fully understand. Not everything we observe makes sense right away. Some exoplanets show light curves that fluctuate unexpectedly, dimming and brightening in ways that don't match simple models. Others appear to have rings or clouds or orbiting debris that cast irregular shadows. One star, nicknamed Tabby's star, dimmed in strange, uneven patterns that sparked global curiosity. Some thought it might be a swarm of comets. Others imagined vast artificial structures, though no evidence supports that idea. Still, the mystery remains. Light curves wiggle and wobble. Transit patterns shift. Some planets show extra dips in brightness before or after they pass in front of their stars. Others change shape, as if wrapped in clouds or trailing dust. We're beginning to decode these patterns. But for now, they remain unanswered questions. Gentle flickers of something we don't yet understand, but can't look away from. There are planets with orbits so wild they nearly escape their stars. Most planets move in quiet, regular loops. But some exoplanets follow long, stretched-out orbits, so elongated that they swing far from their stars before plunging back in, like cosmic comets. These orbits can last hundreds of years. At their farthest point, the planet may receive almost no light or warmth. At their closest, they race past their star, pulled by intense gravity, heated in brief, blinding flashes. These journeys are violent, unstable, and often temporary. Some planets may have been flung into these orbits by collisions, or by passing stars. Others may one day be lost entirely, escaping their systems to drift alone in interstellar space. They are cosmic exiles, barely bound, dancing on the edge of gravity's grip. Their paths are unpredictable, their futures uncertain, but still, they orbit, each pass a reminder of how dynamic and dramatic the life of a planet can be. Some exoplanets orbit burnt-out stellar corpses called white dwarfs. After a star like our Sun dies, it leaves behind a white dwarf, a small, dense ember of what it once was. These stars no longer fuse hydrogen. They don't shine with the energy of youth, but they remain hot and bright for billions of years. And around some of these stellar remnants, we've found planets. Some are close in, surviving unimaginable changes as their star ballooned into a red giant and collapsed. Others may have formed later from leftover debris. The environment is extreme. Radiation can be intense. The gravity near the white dwarf is crushing. But even here, planets persist. Some may even lie within the marrow band where temperatures are right for liquid water. These planets orbit the dead, but they're not dead themselves. They're survivors, echoes, proof that even in the aftermath of stellar death, the story of planets may go on. Others may have formed from the remains of destroyed worlds. In the chaos of a young solar system, collisions are common. Planets can be shattered, moons torn apart, and debris scattered across space. Sometimes from this wreckage, new worlds form, built from the remnants of earlier ones. We've seen hints of this in the dusty disks around some stars, where ring-shaped gaps suggest collisions or ongoing construction. Some exoplanets may be the cause of once larger planets, stripped of their atmospheres. Others might be aggregates, assembled from fragments, fused by gravity and time. These are recycled worlds, not born whole, but rebuilt from the pieces of something else. Their surfaces may be rough, scarred, or molten. Their orbits may be tilted or eccentric, but they exist, and they remind us that destruction isn't always the end. Sometimes it's just the start of something new, stranger, rougher, and more resilient than before. There are planets that may have once been part of another star system. Planets form around stars, that much we know. But over the long life of a galaxy, stars and their planets don't always stay together. Gravitational encounters, close flybys, or chaotic cluster dynamics can fling planets from one star system into another. Some exoplanets may have started their lives orbiting one star and ended up captured by a different one. These interstellar adoptees can end up on odd orbits, tilted, elliptical, or unstable. We can't always trace their origin, but in some cases, their chemical signatures or motions hint that they don't quite belong. They're cosmic immigrants, pulled from one family into another, survivors of stellar drift and gravitational chance. And they remind us that solar systems aren't sealed. They evolve, trade paths, and sometimes gather strangers from the stars. Some exoplanets could be young versions of what Earth once was. When we look at distant planets, we're not just seeing other worlds. Sometimes we're seeing different versions of our own past. Some exoplanets may resemble early Earth billions of years ago, when the atmosphere was thick with carbon dioxide or methane, and life, if it existed, was just beginning to take hold. These young planets might still be forming continents, building atmospheres, or undergoing massive geological change. Volcanic activity, chemical reactions, and extreme weather could shape their futures, just as they did ours. Studying them might help us understand how Earth came to be the way it is. What did our skies look like full billion years ago? What gases filled the air? What storms raged over silent oceans? Some exoplanets may hold the answer, snapshots of an earlier chapter in the story of habitability. Distant, silent echoes of the Earth before we were here to name it. We've seen giant planets orbiting tiny, dim stars. Not all stars are big and bright. In fact, most stars in the galaxy are red dwarfs, small, faint, and long-lived. And around some of these quiet stars, we've found enormous planets. It seems unlikely at first. How could a tiny star host a giant world? But nature, as always, finds a way. In several cases, we've detected Jupiter-sized planets orbiting stars that are barely a tenth the size of our Sun. These massive planets often lie very close to their stars, completing orbits in just a few days. The contrast is striking. A hulking planet looming beside a dim, ember-like star. These pairings defy our early assumptions about planet formation and suggest that even modest stars can host large, dramatic systems. It's a reminder that size isn't destiny. That in the quiet corners of the galaxy, strange and beautiful configurations can still arise. Some stars have planetary systems with dozens of worlds. Our solar system has 8 planets, a comfortable number. but some stars may host many more. Thanks to missions like Kepler and TESS, we've discovered compact planetary systems with 5, 6, even 7 confirmed planets, and signs of more waiting to be detected. These systems are often tightly packed, with planets orbiting much closer to their star than Mercury does to the Sun. In some cases, you could stand on one planet and see another as a bright disk in the sky. Not a star, but a nearby neighbor. Their orbits are often finely tuned, dancing in resonance with one another, like gears in a cosmic machine. These systems challenge our sense of scale, suggesting that planets can form and persist in arrangements very different from our own. And they hint at something deeper, but the architecture of a planetary system may be as diverse as the stars themselves. Other systems appear to have only a single, lonely planet. At the other end of the spectrum are systems with just one known planet, a solitary world circling its star with no companions in sight. We don't know whether these planets formed alone, or whether other worlds were ejected, destroyed, or simply too small for us to detect. But the result is the same: a single planet, tracing its orbit in silence, without the gravitational influence of nearby siblings. These lonely worlds may have very stable or very chaotic histories, depending on how they formed. Some might be gas giants in wide, slow orbits. Others are small, rocky planets hugging their stars closely. The skies of such a world might feel vast and empty. No nearby planets rising like moons. No gravitational harmonies shaping the seasons. Just one world and one sun moving through the dark. It's a quiet kind of beauty, a solitary rhythm in the vastness. Some exoplanets appear to be shrouded in thick steam. Imagine a planet with a surface lost beneath clouds of vapor. Not clouds like Earth's, but dense, swirling layers of hot steam. Some exoplanets may have thick atmospheres made almost entirely of water vapor, created by intense heat that causes oceans to boil and rise. These steam worlds likely orbit close to their stars, where temperatures soar and water cannot remain liquid on the surface. The result is a planet wrapped in fog, invisible below the cloud tops. From space, they might appear featureless, glowing dimly through the mist. Inside, it could be a churning chaos of pressure, heat, and chemistry. Some may still hold liquid water deeper down, or even a rocky surface far below the haze. These are worlds in transition, where atmosphere and ocean blur into one, and the boundary between sky and surface disappears into vapor. There are planets where ice might behave like rock. On Earth, ice is fragile. It melts in your hand and cracks under pressure. But on some exoplanets, especially those far from their stars or deep within thick atmospheres, ice can become something entirely different. Under intense pressure and low temperatures, water can crystallize into exotic forms, dense, heavy, and solid as stone. These high-pressure ices, like Ice the Seventh or Ice X, don't melt easily. They may lie beneath thick oceans or deep inside icy super-Earths, forming hard layers that behave more like rock than frozen water. On such planets, glaciers may flow slowly under their own weight or sit motionless for eons. Mountains could be made of ice that never melts. The boundary between water and geology becomes blurred, and beneath those solid ice crusts, liquid oceans may still churn, kept warm by internal heat, hidden under miles of frozen crystalline pressure. Some worlds could be covered in exotic ices of ammonia or methane. Not all ice is made of water. On cold exoplanets, especially those in the outer reaches of their systems, temperatures drop low enough for other substances to freeze. Ammonia, methane, nitrogen, gases that are invisible and harmless here on Earth, can condense into ices that coat the surface of a planet in pale blue, pink, or yellow frost. These exotic ices may form smooth plains, jagged ridges, or glittering fields beneath a dim sun. Some may slowly sublimate into thin, drifting atmospheres. Others might be stable for billions of years. These planets could resemble Pluto or Neptune's moons, but on a much grander scale, massive frozen worlds where chemistry writes the landscape. The air might be faint and strange, the light dim and distant. But in their stillness, these icy planets are among the oldest and most enduring travelers in the galaxy. We've discovered planets in the star clusters where stars are born. Most stars are born in clusters, crowded nurseries where hundreds or thousands of stars ignite within great clouds of gas. For a long time, we weren't sure if planets could form in these chaotic environments. The gravity, radiation, and close encounters with other stars might make it too difficult. But now, we've found planets even here, in the crowded neighborhoods of starbirth. These exoplanets may orbit their stars while nearby suns blaze with ultraviolet light. They may form quickly or struggle to hold onto their atmospheres. Some may be ejected early, becoming rogue planets. Others manage to stay. Their skies would be full of stars, brighter and more numerous than anything we see from Earth. It's a more dangerous environment. But life and planets seem to find a way, even in the busy, glowing halls where stars themselves are just beginning to shine. Some exoplanets formed in environments we never thought possible. When scientists first began finding exoplanets, they expected them to resemble the solar system, rocky inner worlds, gas giants farther out, gentle orbits, quiet stars. But what we've discovered instead is far stranger. Some exoplanets formed in binary or trinary star systems. Some orbit pulsars, rapidly spinning remnants of exploded stars. Others formed in metal-poor environments where planet formation was thought to be unlikely. In every case, nature proved more inventive than theory. Planet formation, it turns out, is not fragile. It's opportunistic. Wherever there is material, gravity gets to work, pulling, clumping, colliding, shaping. Even in the aftermath of cosmic violence. Even in the sparse outskirts of a system. Even around stars that seemed too unstable, too faint, or too crowded. Planets appear. They don't need perfect conditions. Just time, dust, and the quiet patience of gravity. We've detected planets around stars just a few million years old. Stars live for billions of years, but some planets begin forming almost immediately after their stars ignite. In several cases, we've found planets orbiting stars that are just a few million years old, cosmic infants, still wrapped in the remains of their birth clouds. These stars are young, volatile, and often surrounded by disks of gas and dust. Within those disks, planets begin to grow. Dust grains stick together. Clumps become rocks. Rocks become worlds. Some of these newborn planets are still glowing with leftover heat. Others may be pulling in material, growing larger by the day. Their orbits may still be shifting. Their atmospheres may not yet be stable. But they're real, worlds in progress, still taking shape under the light of a very young sun. They remind us that planet formation is not just a theory. It's something we can watch, right now, in real time. Some planetary systems are older than the Earth itself. Earth formed about 4.5 billion years ago. But we've discovered exoplanetary systems that are much older, as old as 10 or even 11 billion years. These planets have been orbiting their stars since long before our sun was born. They've survived galactic mergers, stellar outbursts, and billions of orbits without being destroyed. One such system, Kepler 444, hosts 5 small rocky planets. The star is more than twice as old as the Sun, and yet its planets are still there, circling steadily. These ancient systems show that planets formed early in the universe's history, even when heavy elements were rare. They're time capsules, leftovers from the early universe, holding clues about what the first planetary systems were like. If life had time to arise there, it could be unimaginably old. We may be newcomers in a galaxy already filled with ancient, quiet worlds. There are planets with masses measured in tens of Jupiters. Some exoplanets are enormous, so massive they stretch the definition of what a planet even is. These giants are often 10, 15, or even 20 times the mass of Jupiter. They blur the line between planet and brown dwarf, objects too small to ignite into stars, but too large to be typical planets. These supermassive worlds often orbit far from their stars, glowing faintly with retained heat. Some may have dense cores. Others might be almost entirely made of hydrogen and helium, with atmospheres thousands of miles thick. Their gravity would be immense. Their weather systems could span entire hemispheres, and any moon orbiting them might itself be large enough to support life. These are the heavyweights of the planetary family, strange, slow-burning giants that challenge our sense of scale and possibility. Not failed stars, not oversized planets, but something unique and quietly colossal. Some worlds might be dense enough to crush iron. Planets come in all sizes and all densities. Some are so light they float in water. Others are so compact their interiors press together with unimaginable force. We've found rocky exoplanets that may be twice as dense as Earth, or even more. Their surfaces might seem familiar, solid, cratered, maybe mountainous, but beneath, the pressure climbs rapidly. In some cases, it could be enough to compress iron into new, exotic forms. These planets may have huge metallic cores, stronger gravity, and shorter planetary radii, despite their mass. They're small but heavy, the compact remnants of larger systems, or the result of unique formation histories. Walking on one would feel strange. The pole beneath your feet stronger, heavier, unfamiliar. These worlds are reminders that not all planets are gentle spheres. Some are tightly wound, compressed by gravity into iron-rich mysteries waiting in the dark. We found planets so lightweight they could float in water. In contrast to the dense, iron-heavy worlds, some exoplanets are remarkably fluffy. These are low-density gas giants, planets with large diameters but very little mass. One famous example is Saturn. which is the least dense planet in our solar system. But some exoplanets go even further. With densities lower than wood, they're made mostly of gas, and if you could find an ocean big enough, they would float. These puffy planets often orbit close to their stars, where heat causes their atmospheres to expand dramatically. They may have small, dense cores hidden beneath vast, transparent skies. Their clouds might be thin and high, their winds slow and drifting. They're enormous, yet fragile, worlds that seem more like bubbles than spheres. Delicate giants drifting in the heat of their stars, held together by the gentlest pull of gravity and gas. Some planets may have lost their atmospheres long ago. A planet's atmosphere is a fragile thing, and over time, it can be stripped away, blown into space by solar wind, radiation, or impacts. Some exoplanets, especially small rocky ones near their stars, may have once had thick atmospheres, but lost them billions of years ago. We've seen signs of this in the spectral fingerprints of certain planets, where little or no atmospheric absorption is detected. The causes can vary. A weak magnetic field might leave a planet unprotected. A violent stellar youth could blast the air away. Or gradual erosion over time could thin the skies to nothing. What remains is a bare, airless world, exposed rock, lifeless plains, and perhaps the fossil imprint of what once was. These are planetary ghosts, stripped down to their cores, circling in silence. And they remind us that even planets can be weathered by time. Others are still actively gaining mass from their disks. Planet formation doesn't end in an instant. Around young stars, swirling disks of gas and dust can linger for millions of years. And in that time, planets continue to grow. Some are still gathering material from these protoplanetary disks, pulling in gas, dust, and rock as they orbit. We've seen direct evidence of this, capturing glimpses of planets in progress glowing in infrared light, still warm from their birth. Spiral patterns in the disk, gaps carved by gravity, and bright clumps of material suggest ongoing formation. These baby planets may still be hot and unstable, their surfaces unfinished, their atmospheres thick and turbulent. We're watching them in the act of becoming, not finished worlds, but places still forming their identities. It's a rare and beautiful thing to witness the birth of a planet, and to know that in the quiet swirl of dust and light, something new is taking shape. We've witnessed the destruction of a planet in real time. Planets are often thought of as permanent, but in some cases, we've seen them vanish. One candidate, observed by the Kepler Space Telescope, appeared to dim and flicker in a way that suggested it was shedding mass, leaving behind a dusty tail as it orbited its star. The planet, likely small and rocky, was being roasted by intense heat and slowly eroded, its material vaporized and swept away. In another system, astronomers spotted what may have been a planet colliding with something large, possibly another planet, producing a sudden bright flare of infrared light. These aren't just theories. They're events we've observed, the last chapters of a planet's story, playing out in real time. Some planets are born before our eyes. Others vanish before we can understand them. Creation and destruction, side by side, in the quiet machinery of the cosmos. Some exoplanets might be covered in metallic snow. On Earth, Snow is made of ice, soft, light, and familiar. But in the atmospheres of certain exoplanets, especially hot gas giants, snow might be made of something much stranger. Metals like titanium and iron can exist as vapor high in the atmosphere, condensing into droplets as they cool. In the right conditions, those droplets could solidify and fall, forming clouds and even snow made of metal. The snowflakes wouldn't look like Earth's, more like tiny shards or crystals, heavy and glittery. On some planets, aluminum oxide could form high-altitude clouds, leading to snowfall made of minerals found in sapphires. These metallic snows might never reach the surface, vaporizing on the way down. But above, in the high skies, they drift quietly, a shimmer of falling metal beneath alien suns. Strange weather, shaped not by water, but by heat, pressure, and elements we usually find in stone. There are planets trapped in tight gravitational dances. Some planetary systems are more like choreography than chaos. We've discovered exoplanets caught in precise interlocking orbits, gravitational dances where each planet moves in rhythm with its neighbors. These are called mean motion resonances. For example, one planet might complete exactly 2 orbits for every 3 of another. These patterns aren't random. They're the result of long interactions, where gravity gently nudges each planet into a stable, repeating path. These arrangements can prevent collisions, stabilize orbits, and allow many planets to exist close together. In systems like TRAPPIST-1, with 7 rocky planets orbiting a small star, we see this harmony in action. It's as if the planets are keeping time, moving through space with a shared rhythm, a quiet, cosmic clockwork. These dances may last for billions of years, their patterns preserved long after we're gone, their balance held in the stillness between the stars. Some systems appear unstable and may collapse in the future. Not all planetary systems are harmonious. Some seem precariously arranged, with orbits that tug, stretch, or tilt over time. These systems may appear stable now, but gravitational simulations suggest they could unravel in 10 million years, 100 million, or more. Planets might be ejected. Orbits might shift. Some may spiral into their stars. Others could crash into each other, triggering cataclysmic collisions. These are unstable systems where planets teeter on the edge of balance. Often they formed through chaotic events, migrating giants, close encounters, or ancient disruptions. What we see now may be just a snapshot of a system in slow collapse, like a spinning top that hasn't tipped yet. Even the universe has its fragile arrangements, places where gravity's delicate work may one day come undone. And the planets, for all their size and silence, are not immune to falling. We've found planets with extremely tilted orbits. Most planets orbit near the same plane, like flat disks around their stars. But some exoplanets don't follow that pattern. Their orbits are tilted, sometimes steeply, sometimes wildly off-axis. In extreme cases, they orbit at sharp angles compared to their star's equator, or even perpendicular to it. These tilted orbits may be caused by gravitational interactions with other planets, nearby stars, or ancient collisions. Some planets were likely born in the usual way, then kicked off course by later events. These tilted orbits can affect seasons, climate, and stability. They also hint at dramatic pasts, histories of motion and disruption where gravity rewrote the script. From afar, we see only the current path. But tilt is a clue, a subtle lean that tells us a planet's story isn't simple. It turned, it shifted, and now it moves in defiance of the ordinary. Some planets spin backwards compared to their orbits. Planets don't just orbit, they spin. And for most, that spin matches the direction of their orbit around the star. But some exoplanets do the opposite. They orbit one way and rotate the other. This is called retrograde rotation, and it's likely caused by dramatic events, collisions with other planets, tidal interactions, or strong gravitational encounters that flip the axis. We've even seen planets with retrograde orbits circling their star in the opposite direction of its spin. These backwards worlds are rare, but real. Their days are reversed. Their weather systems spin in unfamiliar directions. Sunrises and sunsets happen in the opposite order. If you stood on one, the sky might feel subtly off, the rhythms of light and time moving against the flow. These planets don't follow the rules. They're the rebels of the galaxy, slowly spinning against the current of their stars. We've measured the winds blowing across entire alien worlds. Even without seeing them directly, we can measure the winds of exoplanets, and they are fast. In some cases, extraordinarily fast. Using precise spectroscopic techniques, astronomers had detected winds on gas giants moving at over 5,000 miles per hour, fast enough to cross a continent in under an hour. These winds are often driven by intense temperature differences between a planet's day and night sides, especially for tidally locked planets where one side always faces the star. The heat creates pressure gradients, and the atmosphere flows, rushing around the globe in a giant jet stream. Some planets have equatorial winds that carry heat from the day side to the night side. Others may have storms that circle the planet endlessly. We can't feel these winds. We can't hear them. But in the way starlight shifts and flickers, we see their movement, a whisper of weather from a world far away. Some exoplanets are bombarded by intense stellar flares. Not all stars are gentle. Some, especially young red dwarfs, release powerful flares, sudden bursts of radiation that can be thousands of times stronger than anything our sun produces. And planets orbiting close to these stars can get caught in the storm. These exoplanets may be bombarded regularly, their atmospheres blasted by ultraviolet and X-ray radiation. If they have magnetic fields, they might be shielded. If not, they risk losing their air, stripped away, molecule by molecule. We've seen stars like Proxima Centauri flare dramatically and wondered what it might mean for the planets nearby. Could life survive such violent energy? Could an atmosphere recover? Or would the surface be forever scarred by the light of a sun too young and too wild? These flare-bombarded worlds remind us that habitability isn't just about distance. It's also about stability and the temperament of the star you call home. Others bask in the calm glow of quiet red dwarfs. Not all red dwarfs are active. Some are remarkably quiet, stable, slow-burning stars that emit gentle light for trillions of years. Around these stars, planets can orbit close enough to receive steady warmth without being blasted by flares. These calm red dwarfs are some of the most promising places to search for life. Their habitable zones are small but stable. A planet in this zone might be tidally locked, with one side in endless day and the other in endless night, but the climate could still be mild, especially around the twilight ring between light and dark. Life, if it arose, might have billions of years to evolve, undisturbed. These stars don't rush. They live long, quiet lives, and the planets they host may be among the oldest, most enduring, and most gently lit places in the galaxy, slowly turning beneath a peaceful, ruby-colored sun. Some planets might be wrapped in auroras that never end. Auroras, those glowing curtains of light near the poles of Earth, are caused by charged particles interacting with our magnetic field. But on some exoplanets, auroras could be far more powerful and far more permanent, especially for planets orbiting close to active stars with strong magnetic fields of their own. Auroras might stretch across entire hemispheres or ring the planet in continuous bands of color. These lights could be visible not just at the poles, but around the equator, a glowing electric dance across the sky. If the planet is tidally locked, the day side might blaze with starlight, while the night side glows with auroral fire. And on gas giants with huge magnetic fields, the auroras might be visible from space, green, blue, or purple arcs shimmering across the clouds. These are not quiet skies. They are alive with light, whether shaped not just by air, but by stars. We've detected hints of clouds made of vaporized rock. On some of the hottest exoplanets, the atmosphere is so extreme that rock itself can vaporize, rising as gas, condensing into clouds, and forming particles suspended in the air. These mineral clouds might include silicates, aluminum oxide, or other compounds usually found in stone. Using spectroscopy, we've seen signs of these strange clouds, absorbing and scattering light in patterns unlike anything on Earth. They could create shimmering hazes, metallic storms, or skies tinted yellow, gray, or even blood red. On some planets, the upper atmosphere may be filled with sand-like dust, blown by supersonic winds. These clouds aren't soft or familiar. They are the product of heat and gravity, forging strange weather from solid matter. It's hard to imagine, but it's real. On these worlds, the sky is not made of water. It is made of rock, ground down to mist, drifting high above the surface. Some planets might be slowly falling into their stars. Orbits aren't always permanent. For some exoplanets, especially those very close to their stars, gravitational interactions and tidal forces can cause them to spiral inward over time. Slowly, silently, these planets lose altitude, their orbits shrinking bit by bit, year by year. Eventually, they may fall into their stars, consumed in a final flare of light and heat. We've observed signs of this process. Planets with decaying orbits, with periods shortening by fractions of a second over time. The end may be millions of years away, or only thousands. But it's inevitable. Some planets, once stable, are now doomed to vanish, swallowed by the very stars that once gave them warmth. These are worlds in slow descent. Their skies may still be bright. Their days may still pass normally, but above them, gravity is pulling, and the clock is quietly ticking. Others are being flung outward into interstellar space. At the opposite extreme are planets that don't fall inward. They are thrown outward, ejected from their systems entirely. This can happen during the early days of a planetary system, when giant planets interact gravitationally. A close encounter can give a planet enough velocity to escape its star's pull and become a rogue, a free-floating world drifting alone through interstellar space. These rogue planets are hard to find. They don't emit light, and they don't orbit anything. But with powerful infrared telescopes, we've detected a few. Some may be Jupiter-sized. Others could be Earth-like, but frozen solid. Without a star, they are cold, dark, and solitary. And yet, some may still hold internal heat. Some may even host subsurface oceans, warmed by radioactive decay. These are the ultimate wanderers, cast out, unbound, but still planets in every sense. Worlds adrift, carrying secrets we may never hear. There are exoplanets with orbits that stretch across entire systems. Most planets orbit fairly close to their stars, at distances where light, warmth, and gravity maintain a delicate balance. But some exoplanets follow orbits that stretch across vast expanses, looping through their systems on long, slow paths. These wide-orbit planets may take hundreds or even thousands of years to complete a single trip around their star. Some lie so far out that they barely remain gravitationally bound. Others move in elliptical orbits, swinging close to the star before sailing back into the dark. These extended paths may have formed through planetary migration, all as the result of violent encounters in the past. We've even spotted potential planets orbiting hundreds of astronomical units away, so distant that their stars are just bright specks in their skies. These worlds drift on the edge of their systems, nearly free, tracing orbits as wide and slow as time itself. Some planets exist in cosmic Goldilocks zones, not too hot, not too cold. Somewhere between the furnace of a star and the frozen edges of space lies a narrow, precious region, the habitable zone. Here, temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. Earth is in this zone, and so are a growing number of exoplanets. They orbit at just the right distance for water to remain stable, one of the key ingredients for life as we know it. But being in the Goldilocks zone isn't a guarantee of habitability. A planet's atmosphere, rotation, and surface conditions all play a role. Still, it's a good place to start. These planets are among our best candidates for life. And whether they're rocky, ocean-covered, or wrapped in clouds, they lie in the same sweet spot we call home, bathed in gentle light, balanced on the edge of possibility. We've spotted planets that might have Earth-like temperatures. Some exoplanets don't just sit in the habitable zone, they seem to have surface temperatures close to Earth's. These temperate planets are especially intriguing. They orbit quietly, receiving the right amount of starlight to keep them from freezing or boiling. Their estimated equilibrium temperatures suggest the possibility of water, moderate climates, and perhaps even familiar weather patterns. Planets like Kepler 442b and TOE 700d are among these promising worlds. We don't yet know if they're truly Earth-like. Their atmospheres, if they have them, remain mysterious. But temperature is a crucial clue, a gentle hint that these planets might not be too alien. They might have calm skies, winds that blow across oceans, or clouds that gather in the evening light. They might be warm enough for rain and quiet enough for life to grow. We can't see them up close, but we can imagine standing there under a familiar, foreign sky. Some exoplanets could have entirely alien forms of weather. Weather is a reflection of a planet's chemistry, temperature, and atmosphere, and when those ingredients change, so does everything we think we know. On some exoplanets, the weather may be entirely alien. There might be clouds made of molten metal, and rain composed of molten glass or liquid methane. Winds could reach tens of thousands of miles per hour. On colder planets, it might snow ammonia. On hotter ones, the air might shimmer with silicate dust. The colors of the sky could be red, yellow, or pitch black. Lightning might strike through clouds of vaporized rock. Storms could last centuries. Some planets might have permanent jet streams that never shift. Others may experience sudden planet-wide weather events triggered by flares from their star. These are not Earth-like climates. They are weather systems built from unfamiliar physics, beautiful, terrifying, and quietly unimaginable. Others might be home to ice volcanoes or subsurface oceans. Not all geological activity is fiery. On some exoplanets, especially cold, icy ones, volcanoes may erupt not with molten rock, but with slushy mixtures of water, ammonia, or methane. These cryovolcanoes are known from moons in our own solar system, like Enceladus and Triton, and it's likely they exist on distant exoplanets too. Instead of lava, they spew cold liquids into the air, which then freeze and settle back down. Beneath the surface, hidden oceans might remain warm from internal heat, protected by thick layers of ice, sealed away for billions of years. These underground seas could harbor complex chemistry, maybe even life. The surface may be frozen and still, but deep below, the planet is alive with quiet motion. Cracks open, water rises, ice flows like rock. In the silence of the deep, something stirs, a hidden ocean, dreaming beneath a frozen world. Some worlds lie in the quietest corners of the galaxy. The Milky Way is full of motion, stars orbiting the center, clouds of gas collapsing into new suns, planets spinning through space. But some regions are quieter. In the outer edges of the galaxy, far from the crowded center and the spiral arms, stars and their planets move more slowly, in greater solitude. These are the galactic suburbs, dim, still, and ancient. Some exoplanets orbit stars in these peaceful zones, where radiation is low and stellar encounters are rare. These planets may have stable orbits for billions of years. No nearby stars to disrupt them. No tidal forces to shift their paths. Just gentle, endless turning under faint starlight. Life, if it exists, would have time to evolve, to adapt, to endure. These worlds may be cold and far away, but in their silence, there's a kind of cosmic shelter, a quiet where something lasting could begin. Others speed through chaotic, crowded starfields. Not every planetary system lives in peace. Some form in dense regions of the galaxy, near the bulge, in spiral arms, or in globular clusters packed with stars. In these environments, stars pass near one another more frequently. Gravity pulls. Orbits shift. Planets may be tossed into strange paths, or even stolen by passing stars. A planet in one of these crowded starfields might see dozens of suns nearby, bright, close, and always in motion. The night sky could glow with constant light. But with beauty comes risk. A gravitational nudge from a nearby star might destabilize a planet's orbit. Radiation from a supernova could strip away its atmosphere. These planets live on the edge of chaos, speeding through crowded space, dodging catastrophe with every orbit. And yet, they survive, holding on, circling their stars like dancers in a tightly packed, ever-shifting ballroom of fire and light. We've discovered planets orbiting pulsars, dead stars that pulse with light. Pulsars are the remnants of massive stars that exploded in supernova, dense, rapidly spinning neutron stars that beam light like lighthouses. For a long time, no one expected planets to survive such violent events. But astonishingly, some do. In fact, the first confirmed exoplanets ever discovered were found around a pulsar, PSR B 1257 plus 12. These planets orbit a star that is long dead, pulsing steadily as it spins dozens of times per second. Their origin is still debated. They may be survivors of the original planetary system, or they may have formed afterward from fallback material that circled the pulsar and coalesced into new worlds. Either way, they are among the strangest planets we know, silent companions to a collapsed core, circling a star that no longer shines with fusion, but still pulses with the afterglow of death. Planets around the dead, ghost worlds orbiting ghosts. Some planets may have survived the explosions of nearby supernova. Supernova are among the most powerful events in the universe. Brilliant, violent stellar deaths that can outshine entire galaxies for a brief moment. When they happen, they can destroy everything nearby. But some exoplanets may have endured these cosmic blasts. If a star in a binary system explodes, the surviving companion and its planets might remain, scorched, but still orbiting. In other cases, a planet may have formed later from the debris. Astronomers have found heavy elements, like iron and calcium, in the atmospheres of certain white dwarfs, a sign that planets once orbited them, and perhaps still do. If any world remained after such a blast, it would carry the imprint of catastrophe. Its surface might be seared, its air changed forever. And yet it would still exist, a planet that lived through a star's final breath, a witness to cosmic death and to survival. There are worlds with atmospheres rich in exotic gases. Earth's atmosphere is familiar, mostly nitrogen, with a touch of oxygen, water vapor, and carbon dioxide. But exoplanet atmospheres can be far stranger. Some are filled with hydrogen and helium, like mini gas giants. Others contain methane, carbon monoxide, or thick clouds of sulfur-based compounds. One exoplanet, HD 209,458b, shows signs of escaping hydrogen, its atmosphere puffed out and drifting into space. Another has spectral hints of titanium oxide in its skies. These gases affect everything: temperature, color, weather, even what kind of light the planet reflects. Some atmospheres may be hot and transparent. Others may be murky and choking. And some may look clear from afar, but hide layers of chemical complexity below. With every new discovery, we expand our understanding of what an atmosphere can be. Air, it turns out, is not always breathable, or blue, or even soft. Sometimes it's metal. Sometimes it burns. Some planets might be rich in carbon or poor in oxygen. On Earth, oxygen dominates our biology. But in other parts of the galaxy, carbon may be king. Some exoplanets may have formed in regions with more carbon than oxygen, leading to chemistry we've barely begun to understand. These so-called carbon planets could be rich in graphite or diamond, with mountains of pure carbon or oceans of hydrocarbons. Their skies might hold methane instead of water vapor. Their soils might sparkle with unfamiliar minerals. Conversely, some planets may be oxygen poor, with iron-rich surfaces and carbon-based clouds. Life, if it exists, would be very different. The rules would change. The elements would tell different stories. These planets challenge our assumptions. Not every world will resemble Earth. Some will be forged from different ratios, shaped by different conditions, built on different foundations. And yet, they too are real. Places where alien chemistry writes a different version of what it means to be a world. We've just started to look for biosignatures on distant worlds. A biosignature is a clue, a hint that life might be present, even from light years away. On Earth, our atmosphere contains oxygen, methane, and water vapor, in patterns that are hard to explain without biology. And now, astronomers are beginning to look for similar patterns on exoplanets. Using advanced telescopes, we can split starlight into spectra and search for the fingerprints of life-related molecules. It's delicate work. Clouds, temperatures, and star type all influence the results. But already, there are intriguing candidates. Some planets show signs of water vapor. Others have suspicious amounts of carbon compounds. In the years ahead, new missions will search even deeper for ozone, chlorophyll-like signatures, or chemical imbalances that suggest something living is at work. We haven't found life, not yet. But we are listening more carefully than ever, watching for the tiniest flicker of biology in the silence between stars. Some exoplanets could be covered in dust storms that last for years. On Earth, dust storms are temporary, brief, sweeping events that come and go with the seasons. But on some exoplanets, especially those with dry atmospheres and thin clouds, dust storms may never fully stop. Winds blow across barren landscapes, lifting fine particles into the air, swirling them endlessly. Some exoplanets may be so dry and hot that global dust storms last for years, or even longer. The skies would turn copper or brown. The sun would fade behind drifting haze. From space, the planet might look smooth and soft, its features buried beneath ever-moving clouds of grit. These storms affect temperature, light, and even atmospheric chemistry. They may shape the planet's climate entirely. And if any life existed there, it would have to adapt, not to rain or snow, but to an endless hush of dust, stirred by slow, relentless wind. Others might reflect so much light, they shine like beacons. Some planets are almost invisible, dark, muted, hard to detect. But others are brilliant. Certain exoplanets reflect huge amounts of starlight, either because of high reflective clouds or smooth surfaces covered in ice or vapor. A planet like Kepler 7b, for instance, may be covered in silicate clouds that gleam like polished stone. Others may have vast reflective layers of metal oxides or exotic compounds. These worlds act like mirrors, glowing with borrowed light, visible even from hundreds of light years away. Their albedos, a measure of reflectivity, are among the highest we've ever seen. In some cases, these planets outshine their stars in certain wavelengths. They don't make their own light, but they echo it, brighter than Venus, brighter than snow. These planets don't hide in the dark. They shimmer, they glow, and they remind us that sometimes it's reflection, not heat, that makes a world luminous. Some planetary systems resemble scaled-up versions of our own. Not every exoplanet system is chaotic or strange. Some, surprisingly, look a lot like home, but bigger. We found systems where smaller rocky planets orbit closer in, while larger gas giants sit farther out, like a stretched version of our solar system. Some even include asteroid belts or icy outer zones, much like our Kuiper belt. These similarities suggest that certain laws of planetary formation may be universal. Gravity arranges the dust and gas. Rocky worlds take shape near the star, where it's warmer. Gases condense farther out. The results feel familiar, but on a grander scale. Perhaps Earth isn't so unique. Perhaps other solar systems follow a similar rhythm, echoing ours across the galaxy. We may not know if they have moons, oceans, or life. But when we look at them, we see a structure we recognize. A reminder that our place in the cosmos may not be so rare after all. Others follow rules we're only beginning to understand. And yet, many planetary systems break every rule we thought we knew. Gas giants that orbit closer than Mercury, planets on tilted, elliptical, or even backwards orbits, stars with more planets than we thought possible, moons that may outsize planets, or planets that migrate from their birthplaces, shifting the entire architecture of a system. These odd arrangements defy our expectations. They don't fit the tidy models of how planets should behave, and they challenge us to rethink the basics. Maybe planet formation is less orderly than we imagined. Maybe it's wild, creative, flexible. Each new system we find adds another variation. Each planet tells a new version of the same story. The more we discover, the more complex the picture becomes. And the more we realize, the universe is not following a script. It's improvising, building worlds we never thought to imagine. We're building telescopes to image these worlds directly. Until now, most exoplanets have been detected indirectly, by the way they dim starlight or shift it slightly as they orbit. But now, we're entering a new era. Engineers and scientists are building powerful telescopes designed to see these worlds directly, not just infer their presence, but actually photograph them. These instruments will use coronagraphs to block out starlight, or giant star shades to create artificial eclipses in space. The goal? To glimpse an exoplanet as a small, faint dot beside the brilliance of its star. From that dot, we can extract light, study its atmosphere, even search for signs of life. Telescopes like the Nancy Grace Roman Space Telescope and future missions like LUVOIR or HAB-X aim to do what once seemed impossible. Take portraits of alien worlds. Soon, exoplanets will no longer be shadows or signals. They'll be places seen with our own eyes. Some planets may already have been photographed in blurry detail. It's already begun. Using extreme precision and clever techniques, astronomers have directly imaged a few exoplanets, huge gas giants far from their stars. These images are not detailed. They don't show continents or clouds, just tiny specks of light, blurry and faint. But they are real. We've captured the glow of heat from a planet still cooling after formation. We've watched distant gas giants orbit slowly over the years, confirming their motion through space. The first of these images, like those of HR 8799 planetary system, mark a new chapter in astronomy. They are crude by modern standards, but they are history. The first time humanity has seen light from a world orbiting another star. As our instruments improve, so will the images. Someday we may see weather systems, oceans, or even signs of life. For now, we have a blur, a whisper, a start. The search for life often begins with exoplanets. When we imagine life beyond Earth, we think of planets, places with air, water, sunlight, and time. And so, the search begins with exoplanets. We look for those in the habitable zone. We scan for oxygen, methane, and other chemical signs of biology. We study their orbits, their stars, their atmospheres. Every detection brings questions. Could this planet have water? Could it support microbes? Could anything live there? Even the smallest hint, a spectral wobble, a faint absorption line, sends ripples through the scientific world. Because if we find life, it will likely be on a planet, not in a gas cloud or asteroid belt, but on a distant world that quietly turned for billions of years, unnoticed. Exoplanets are our best hope. Our mirrors, our windows, the places we search when we wonder, not just if life exists, but what other stories the universe might be telling. Every new discovery reminds us how strange the universe can be. The more exoplanets we find, the stranger the universe becomes. We expected Earth-like planets. What we found were lava worlds, rogue wanderers, planets with icy rings or molten skies. We found systems with dozens of tightly packed planets, planets that orbit dead stars, planets where weather, chemistry, and gravity dance in ways we never imagined. Each discovery adds a new twist, a new shape, a new possibility. The universe isn't just big, it's inventive. And the planets we've seen so far, just a few thousand, are likely a tiny fraction of what exists. The surprises keep coming. And with each one, we remember, the cosmos is not simple. It's not familiar, but it is endlessly creative. And by exploring these distant worlds, we learn to expand our imagination and find wonder in the unexpected. There may be more planets than stars in the Milky Way. For centuries, we imagined planets as rare, little companions circling stars here and there. But today, the evidence is overwhelming. Planets are everywhere. The average star in our galaxy likely hosts at least one planet, and many have several. That means there may be more planets in the Milky Way than there are stars. Hundreds of billions of worlds. Some are giant, some small. Some hot, some frozen. Many are unlike anything we've ever seen. But the numbers suggest something remarkable, that planetary systems are not special exceptions. They are the norm. The galaxy is not just a field of stars. It's a garden of worlds, each one following its own path, each one a quiet possibility. And somewhere among those billions, some may be blue, some may breathe, some may be waiting. Somewhere out there, a planet like Earth might be waiting. We don't know where. We don't know what it looks like. But the odds are with us. Among the countless stars and their countless planets, there are surely some like Earth, rocky, warm, wet, and alive. It might orbit a small red sun, or a bright yellow one. It might have oceans and forests, or forms of life we'd never recognize. Maybe it's quiet. Maybe it's just beginning. Or maybe it's ancient, with civilizations that rose and fell while Earth was still molten. We haven't found it yet, but we are looking. Every telescope, every mission, every exoplanet discovered brings us closer. And when we finally find that world, that small, distant twin, it will change everything. It will remind us that we are not alone in the quiet, vast dark, that other Earths exist, and that the universe is, after all, a place meant to be shared. And now, our journey draws to a close. We've wandered far tonight, beyond the warmth of our sun, past the edge of familiar skies, into a galaxy filled with silent planets, each one a quiet answer to the question, what else might be out there? We've drifted through dust storms and burning skies, through oceans locked beneath ice, and through atmospheres made of metal, wind, or cloud. We've watched stars flare and fade, seen planets flung into the dark, and imagined life, strange, fragile, impossible, taking root on worlds we'll never touch. And all along the way, one thought has remained. But the universe is not only vast, but full of places. Places with gravity and weather, with histories and futures, with stories still unfolding in the quiet. Each exoplanet we visited tonight, whether it was real, theorized, or barely glimpsed, was a little world of its own. A small gravity well in a sea of starlight. A question wrapped in silence, waiting for us to notice. And maybe that's the wonder of it, that even as you lie here, still and safe, the cosmos is continuing. Stars are shining, planets are turning, and in some far-off sky, a world not unlike our own might be spinning slowly through its night. So, if your eyes are growing heavy now, if your breath has settled into rhythm, if your thoughts have begun to drift like stardust in the dark, you don't need to return. You're already part of this universe, already floating, already home. Thank you for sharing this moment, this quiet voyage among distant worlds. And if it helped you rest, you're always welcome to return, to listen again, to dream again, to keep wandering. And if you happen to still be awake, you can go ahead and watch the next video now. There are always more wonders waiting, more science, more stillness, more stars. But for now, rest. The planets will keep turning. The universe will wait. Good night.